so my name is Julien. Thank you for coming. I will talk about iOS application reverse engineering. So, to do a quick agenda, we'll speak about the architecture, the file formats, the language, the processor, then how to work with App Store binaries, as binaries that you buy on the App Store. And then, what are you looking for when you are reversing such an application? For introduction, I'm a security engineer at SCS3. I'm mostly interested in reverse engineering and OS internals. Even if I got a lot of Apple stuff, I'm not a fanboy. It's just that I think that the Apple products are new territory to explore and to hack and find vulnerability in it. And the goal of this talk is not to present new stuff and don't expect anything about jailbreaking. It's more to open the door and convince you to cross that door and do research on your own in this domain. So just one slide with a few numbers to set the context. The iOS terminals have more than 160 million users, 4,000 million applications available, and 10 billion downloads. So we can say that it's a huge user base, which may attract a lot of attackers, because with more users, we attract more attackers. We have another thing really important, that it's a lot of e-banking applications are becoming available on the App Store. So this means that there is more and more applications which may store sensitive data about you. So of course, Apple set a review process in order to eliminate unwanted application and malicious application. But as they say, they found 10% of the applications that are submitted each week are malicious code. But the problem is that they found 10%. But what about the rest? For example, we had flashlight application, which in fact was an application to do some tethering. So it's not malicious by itself, but it bypassed the review process. And there were another case with Storm 8, which is a game editor who was brought behind in front of a court in order to speak about the fact that their product was stealing some sensitive information about the user. But now, what if you want to check an external application? So beware with the legality of those things in the country. But or if you are in a security team inside a big group and you have some developers which are doing an application that your company will make available on the App Store, and you want to check that what the developer made. You can look at the source code for sure, but you can also do a black box audit. And for example, for the company I'm working, as we are external elevator, we will do some of our customers might ask us to do a black box audit of those kind of applications. And the best reason here is that because it's always fun to learn how to reverse new things. Most of the time, maybe it's not that useful to reverse the application to do the audit, but yeah, the first time I had to do it, it was like a new game and I had to play with and reverse it. This is how it came. So, to start speaking about the file format, the file format is called MacOS or Mac Object. It's a file format used to store executables, libraries, and also condoms. Mac files can be divided in three parts: header, some load commands, and then the data. The headers is a basic structure which start with a magic number, like every file format. The magic number is equal to bit face, the hexadecimal number. Then you have a security type, which is the family of the CPU. It can be Intel, PowerPC, ARM, and so on. And then you have a subtype. For example, in Intel you have the 32-bit processor and 64-bit. And for ARM, we will have ARM version 6 and version 7. So the security type for iPhones will be 12, and security subtypes will be 6 or 7. And then you have other information useful to parse the whole comments. We can use a tool like HTEditor to look at the headers. So here we can see that the magic number is equal to fit face, and we see then the other information. So following this header, we have the load comments. They are used to tell the operating system loader how it should map the different parts of the file into the memory. And also to locate the symbols, tables, and the shared libraries. And another important fact is the context of the main thread, which means the state of the registers, whereas the code execution start, something like that. The last part is the data. We have sections themselves containing sections. The first one is page 0. Its size is equal to 0, but it's used to map the first memory page. You know, when you are using when you have a stakeholder, you're getting a new pointer. In fact, this first memory page is which goes from 0 to 5096 is used to catch those memory errors. Then we have the text segments, which contain executable code and read-only data, and then the data segments and some other segments like the Objective-C segments, which contains data which are used by Objective-C runtime. So you will say it's OS 10 or iOS, they're just a kind of Unix, so I can use my standard Unix tools. That's true, but not always. For example, you can't use OBJDOM. You have to use OTool, which is the same tool, but it works on the macro files. Another particularity about the macro files is that they can be packed in another file in order to support multiple architectures. You know that Mac went to PowerPC to Intel processor, so the executables can be packed into a universal file, which will contain the code for PowerPC, 32 or 64 bytes. And for ARM, we'll have the fast file, which can contain the code compiled for ARM v6 or v7. So next up, the Objective-C language. It's a superset of the C language, which is object-oriented. But there is one big difference with the C++. It's how we call method. And this is something we have to know when we are reversing an iOS binary, because it's used all the stuff. And the same for binary on OS 10. So with C++, we write something like object pointer, then your method and the parameter. On Objective-C, you will write like this line, the object pointer, the method, the first parameter value, then the second parameter name and its value, and so on. So on this point, it's already different when you are writing it. But under the hood, in fact, when you are writing object pointer method, it's translated into something like a call to Objective-C mhdsend with the object pointer and a selector to the method. and then the different arguments. So what is a selector? A selector is a set string. So in this case, this will be translated into output to obviously image.sm, the pointer, and then the string method. Here, in this case, the method is called method. So going one step further, we have the processor. So the processor is named ARM. It's a RISC. It's part of the RISC family. So it's a reduced instruction set computer, which are also called block store architecture. In order to gain speed, most of the processing are not done on memory, but only a few instructions are working on memory. So you use those instructions to load data into the registers, and then you work only on the registers. So this speed up the execution. The instructions are 32-bit length. The length is fixed, except if you activate the term mode, which will reduce the instruction size to 16. So this means that the instruction will take less place, which is useful when you are doing embedded development, and they will also be quicker to execute, but you have a reduced set of instructions. If we look from a user level program, we will have several registers available. There are 15 general purpose registers, going from R0 to R14, and the equivalent of the program component, so EIP on Intel, is called R2. The equivalent of also named EBP on Intel, is R14. And you have also all the flags like you will have on Intel architecture. So as I said, this is a load store architecture, so the instruction can be divided into 3 groups. So the instruction that are used to load information from the memory to the register and back on the side. Then you have the data processing and everything related to control flow. To load from memory and to store from to memory, we will use those 2 instructions, NDR and SCR. For all those instructions, we recommend you the reading of the ARM manual. You can find it on Amazon. It's a book. It describes all the CPU. Everything is specific to the CPU, all the instruction, and how to write a program over it. Then you have also the data processing instruction. We have a instruction like this add. You can also use immediate operands, and you could also use shifted register operands. Like the last example is putting into R3 the value of R2 plus R1 with a left shift on 3. The last kind of instruction is the control flow instruction. So you have the typical branch ladder, so B or BOM for branch always. Then you have the conditional branches, and like in the Intel architecture, you have also the conditional execution. So for example, this add and will only execute if R0 is different from 5. You have also the branch and link instruction, which are used in order to call subroutine or method functions. When you are writing something like beyond subroutine, it's equal to the following steps. R14, which is the equivalent of EBP, will contain the next instruction address, and then the jump is made to the subroutine. The first thing that we are doing in the subroutine is to push the register we are using and this new register, and then at the end we will pop the register, and we can also directly access the program control. This is something that you can't do on 30-bit Intel processor. You can't address EIP directly in assembly. But in RM, you can directly put data, write data into the R15 registers. So another useful thing is the calling convention. So the arguments are stored in the 4 register up to R3. The local variables are stored in R4 to R11, and the return value is stored in R0. To sum it up and review everything I just said, in C++, we write something like the object pointer to the method. We saw that in Objective-C we have to write it that way. It's then translated in pseudo-C equivalent equals to obviously MHSM, the pointer, the string referring to the method name, and then the parameters. And in our RM assembly, this will be translated into those 4 instructions. So you will store the value, and then we'll branch and link to obviously MHSM. So it's you have to know how it works this way. So when you are seeing RM assembly, you can do it backwards. So now about the App Store binaries. The first thing you have to know is that the simulator is only useful when you are developing iPhone applications. As its name said, it's a simulator, not an emulator. And the code which is produced for the simulator is targeted for Intel 32-bit processor and not ERM. So you have to use a jailbroken iOS device, NSL, not talking about jailbreak. But here you have to, and then you install SSH in order to launch command on the iPhone and GDB to debug. So now how to find them? They are, when you are on your Mac or your PC, they are stored into the music folder from iTunes. It's not the location you will search for in the first place. And they are stored as a .ipa file, which in fact are just a zip file, but just rename the extension. If you are looking for them on the iOS device, they will be stored into a bar-online application, then into a folder corresponding to the UID of the application, and then a folder name with the application name.adp. Into that folder, we will find the file required by the application to work, like all its resources and other stuff like the code signature file, and even a screenshot of the first screen, so you think it's loaded quicker than the others. Just before I say that those files can be packed into file binaries, so if we want to work on a specific architecture, then we have to extract the file corresponding to the device we are using. So in our case, I was working with iPhone 3G, so I had to extract the ARM-based 6 binary. So we just have to use the Hippo application and tell them to extract the right binary. And if we check with Auto and to check the headers, we will see that you have the correct magic number, a CPU type of 12, which is ARM, and CPU subtype of 6 for ARM-based 6. So now we have a small program, but it's really easy to overcome it. So there are those binary that you are doing on the App Store are encrypted with a method that is really like the fair play method they are using on the song that you bring on iTunes. So each executable page is encrypted with AES, and then MD5 checksum is computed for all these pages. if you want to check if a binary is encrypted, which is always the case from binary book from the App Store, you can use the content of the LC encryption info command, and if the value of the cryptid option is set to 1, then it means that the binary is encrypted. If you have a jailbroken iPhone, you can check that some of the applications that come with it, like the main application and such application, might not be encrypted. So if we look at our binaries, it was encrypted. We just have to display the log commands with auto and then do correct. So no more to unpack it. Of course, we can use a script. There are many of them on the web, but that's not yet enough. And we want to understand how it works, because it's always easier to use a tool to crack something, to reverse it. But the best way of saying this thing is, okay, the first time I have to do it myself by hand, and then maybe I can use a tool if it's take too long. So we'll use this method. It's really easy. We just have to launch a debugger, set a breakpoint, then run the application, extract the encrypted executable code, and then patch the binary that you have at the beginning. So it's really like when you are reversing a malware, which is packed with simple obfuscation. You just have to look at the GMP and then a register. You put a breakpoint on it, you wait for the decryption to happen, and then you just dump the content of the memory. So, where are we setting this breakpoint? When you are launching a binary on your iOS device, the FAT binary will be run. The architecture-specific binary is extracted from these FAT files and mapped into memory. And then the code will be unpacked, and the start symbol will be called. So we can get the location of the start symbol using NM. And then just to get it. So here we have the start at 2000. So the first step, we just run this program into our debugger. We set a breakpoint, and if we look at the instruction at this address, we see that we have instruction, but they don't mean anything. So there's a correct instruction, but there is no continuity in the execution. Then when we reach the breakpoint, if we dump the same instruction, we will see that they all change. So now we have something that is that means something and with correct instructions. We just have to dump everything. So we'll use the dump command from DB, and we'll use some information like the offset where the code is matched to memory, and the crypt size, which is another option part of the LC encryption info load command. So we just this is the addition to this use at the end. It's don't address plus the size of the data. Now that we have extracted the executable code, we have to patch our initial binary in order to work on it. So the first thing we have to do is to locate this LC encryption info load command and change the value of crypt ID from 1 to 0. So this is not a required step if you just want to do some static analysis, but if you want to repack the binary and then run it on your device, you have to do it, because all code will be unpacked. So if you tell the loader that it's still packed, you will try to unpack it, nothing will work. So to locate it, we have two options. The first one is to write our own math object header parser, so using those include files. And the other option options is to use hexadecimal editor and to search for the hexadecimal representation of this load command. So you have to take care of the Indianness of the load command. So for example, the CND size is equal to 20, which is 14 in hexa. So you have to switch the Indianness in order to construct your pattern. Then we can use an hexadecimal editor, search for this pattern, and we'll find it, and we have to edit the second line. There is a 0001. Here we change the 01 to 00. And if we check again with our tool, we will see that the crypt ID is equal to 0. So now if we wanted to pack it again, we have a binary that's not packed. But the last step is to put the unpacked data back into the binary. So to do it, you just have to use this line of Python. I don't know what language you want to use, but you just have to see that the program set, write the data back, and close the file. Pretty easy. So now we have an unpacked binary, we can work on it, so we can start the reverse engineering. So the first thing we might want to have is the class definitions. So we can use a binary named class.dump, which will extract all the declaration from this binary. And the other thing we will have to deal with is all those calls to RGC MHSM. Because if you want to reverse an application, it's better to have some cross-references. When you are in a function, you want to know where it's called. And with all this asynchronous method, with the name of the method, it's hard to have a cross-reference directly. You have to modify the binary before you can edit. So if we look with class.dump at our binary, we can see that we have the main class, which is derived from UI application delegates, which implements a few methods. We come back to that later. So we use this dump later. And if we start looking at the disassembly, if we look at for example, at the main function, we'll see there is 3 calls to ODC and HSN. And I guess they are pretty meaningful. You can't really work on the binary. So you have two options to modify it. You can patch it by hand, knowing the calling convention and the form of a call to ODC and HSN. We know that there is a reference to the object and then a string representing the method name. So we have to look at L0 and L1. And so if we go backwards in the assembly, we can look at the last value set on those registers and find the correct value. So for the selector, you will find the C string, and for the object pointer, then you have to look into the structure of this reference into memory, and into this structure there is a C string representing the class name. And the other option is to use an IDEA Python script made by Zenmix, and this is really useful to have it because you will patch the binary, and here it's the same disassembly as before, but all the patch, the call to ODC and HSN are replaced by call to object methods. So here we have a call to NS Autobility Pool class with the method app. So now that we have something we can work on, we want to start reversing it. So all the stuff like I said, you can automate all this process, and it was just to know how it was working on the code. So the first thing we want to do when we are reversing a binary is to know where the code execution started. So yeah, the code execution will start at the main class and the start symbol. But then, what will be called? If you look into the start function, you will see that they are calling application did finish launching with options to this example. But they might have all the things, and you might want to know all the different entry points when you're reversing an iOS binary. So when you are developing an application, you have to your main class should be derivated from UI application delegates and should return one of those two methods: application did finish launching or application did finish launching with options. Those are the two methods that will be called when your application is mapped into memory and the user can start interacting with it. Then, if you have multiple views into your application, when each view is displayed to the user, a method named view_didLoad will be called on this view. So those views have to implement this method, and the view will be derivated from UI something control. So we can use the output of class to look for such things. So for example, here we have the podcast app delegate class, which is derivated from UI application delegates. And we see that it's implementing the method finish launching with options. So we can search into the disassembly, and it's one of the starting points and doing the disassembly. Now we might also want to audit all the remote connection the application is making. So the first one we might think of is all the HTTP connections, HTTP or HTTPS. In order to make such connection, the application has to use the NSURL flags. And there are also NSFTP or CF socket create, which are other flags used to call if you want to instantiate sockets or FTP connection. So here, if you search into an application for NSURL, you can see that here we have a call to NSURL URL with string. And if we go back on into disassembly, we can say that the value for the URL is 10.0.2.1/Julien/iPhone.php. So here we can say that this application might be doing a call to this web page, and then we can see what kind of data it's sending to this page and so on. In this case, it was an application. I took the example from Nicolas Serio. He presented it at the Black Hat last year, and I just modified it so when the application is started, it will take all the information and post it on the web page. So here, if you are taking this application and want to do a reverse engineering, you will see that those applications, those information are all taken into a binary blob and then sent to this web page. So I'm pretty sure you all read the Front Offer Institute reports saying that lost your iPhone, man, too bad, you also lost your password. This is partly true because they don't get all the passwords. Some of the passwords can be protected in the keychain using a passcode starting with iOS 4. If you set a passcode on your iOS device, the keychain items can be encrypted with the passcode. It's an additional encryption. So if you want to add items into the keychain and use this option, you have to call the sequitel_add method and set an attribute which is called cassec attribute accessible when unlocked. From this example, we can see that Microsoft is not the only one with very big, long function names, but at least they are meaningful. If you want to store a file and encrypt it, you have to use the option NS file protection complete when you set several attributes on the file. So if you want to have an example, here we can see that the application that is DSM. We have is building a dictionary and it's setting some attributes like the classic attribute accessible after first unlock. So the data that will be stored into the keychain after this call are going to be encrypted with the passcode. So if someone is using the method described into the front of the institute's paper, then they won't be able to get the data. So, as a conclusion, we'll not really say that it's a revolution, but it was only an introduction, like I said at the beginning. It was to give you key points so you can work on it, and yeah, don't be scared by the fact that it's packed or something like that. We saw that it was really easy to get it, even doing it by hand. You can use script if you want. Now it's your turn to grab a debugger and work on some project. There's a lot of things to do, either in the user mode or kernel side of iOS. There are, I'm sure, plenty of vulnerability to search for. Maybe you are involving into auditing iOS application. So I hope this can help you. I have also my Twitter and you can call me videos if you talk about it. That's it.
So the questions and after the voting, time for you.
I know this presentation was maybe 6 minutes long, but why to see it?
First, the question. Who has a question?
Yeah, you gotta get it right. There is a possibility that within one flat binary there are assemblies for two different arms. And at least if I have 6, version 6 plus this 1.7, or are they completely
In one way, I think you can use 6 assembly on 7, but from a universal point of view, it's important to view the source code, but most of the time it's only used for optimization for the compiler. You just say that you're compiling your binary to both architectures, and the compiler will do stuff with specific thing. But maybe someone can hide some execution step into a specific architecture and undo it on the other side.
if he knows which one is that and is checking?
Yeah, I don't know if they're checking both architecture, and I never heard of someone using this technique. So maybe there's something that made it impossible to do with in fact.
Other questions? Otherwise, we can take a look.
So,
you ready?
on what type of processor are running iOS devices? A Intel, MIPS, ARM, iCPU. One of them is clearly coming in the near future.
MIPS.
Yeah, that's right. So we have 0% of binary people saying ICQ in the near future. So what is the name of the binary file format? Yeah, IPR, Micro. what is the name of the dot command related to the encrypted code? Pretty easy. LC encryption info, LC encryption, LC equalized private key, or LC unique thread. The last one. What is error handler? A mode where everything is good. Turns out no. Change instruction size from 2 bytes to 4 bytes, or change from 4 bytes to 2 bytes, or speed up the execution time. So yeah, that was to change the instruction size from 4 bytes to 2 bytes. But actually it's also speeding up the execution time.
Thank you very much.